Hi everybody! The video that you will see now is on my presentation in the Actives 2022 workshop on optical and electrical material for bioapplication. This Active 2022 workshop took place at the Institute of Science of Materials of Barcelona, where I am working now as a postdoc. After that, I explained all the changes and the evolution that the electrochemistry has experimented in order to address the challenges of point-of-care devices for diagnostic. And finally, I ended with my personal results, obtaining at different research centers developing electrochemical biosensors for biomarker detection. I hope that you enjoyed this presentation, and I hope also that it will be useful for you. See you!
Electrochemical analysis in the biomarker detection for clinical diagnosis of disease, addressing requirement toward point-of-care devices. One of the most important approaches of the modern medicine is the development of personalized medicine. The personalized medicine, or precision medicine, refers to the tailor-made prevention, diagnostic, and treatment strategies for individual or patients based on their predicted response or risk of disease. The successful advance of the personalized medicine is closely related with the growing of genetic and genomic, proteomic, and biomarker information, diagnostic and drug delivery, and of course, of point-of-care diagnostic. In this context, the development of diagnostic devices of point-of-care type is mandatory because personalized medicine requires the individualization and decentralization in the diagnostic and treatment of disease. Point-of-care diagnostic has represented a viable way to develop personalized medicine to patients with chronic disease. An score point-of-care is designated to be this powerful analytical tool that such effective diagnostic systems are in demand. Diagnostic testing in general has significantly improved the quality of healthcare. The most of clinical analyses are taking place in centralized laboratories with many facilities and expensive equipment. They require long time of analysis and are carried out by specialized personnel. However, point-of-care are created to be cheap, portable, quick, reliable, and with easy manipulation. Point-of-care analysis is performed on-site without the need for training personnel or specialized equipment. The idea of point-of-care is a sensor device able to generate and answer out after a minimum of volume of sample in a lab-on-a-sheet format with the miniaturization and simplification of the analysis. Electrochemical analysis, a good alternative to implement point-of-care devices. Electrochemical biosensor technology presents many possibilities and benefits to develop point-of-care. First, electrochemical techniques are rapid, quantitative, accuracy, and present extremely low limit of detection. In addition, there are a large variety of electrochemical techniques such as DPV, cyclic voltammetric, EACI, square wave voltammetric, etc. Second, both the cell and the electrode can be integrated and miniaturized for low-cost assembly and mass production. Possibility of produce tailored and customized electrodes by using multiple printing techniques such as inkjet printing, pen plotting, screen printing, 3D printing, etc. Third, the low cost, the miniaturization and the portability of potentiostat and his integration with a smartphone. Successful case of electrochemical point-of-care devices in the market. There are many electrochemical point-of-care devices in the market. The most known case is the glucometer for glucose monitoring in blood. The enzymatic sensor uses integrated screen printing electrodes and embraces all the point-of-care requirements: accuracy, low cost, portable, small sample volume, etc. Oscore electrochemical analysis has experimented many changes to address the necessary requirements to reach the market. For example, the transition since large and heavy equipment toward low-cost, portable, and miniaturized potentiostat. Recently, many research groups have fabricated their customized and portable potentiostat connecting to a smartphone by USB port or Bluetooth. In the same way, Electrode has experimented a miniaturization, integration, and mass production process. Since the fabrication of solar are separated cells and electrodes, to customized microelectrodes take advantage of the several printing techniques such as inkjet printing, screen printing, physical vapor deposition, thermoplastic, etc. All this fabrication technique has made possible to print on paper flexible plastic microscope glass slides at very low cost. Regarding the design and conceptualization of the analysis, it also has moved toward the simplification, shorter time of analysis, the reduction of reagent and analysis steps, and reducing costs in general. In this context, the trend has passed from label sandwich format with a primary and secondary antibody to a label competitive assay and ending in the completely label-free assay. There is an increment in the use of DNA probe and aptamer as biorecognition molecule, or in the use of synthetic biocaptor like molecular imprinted polymer or inorganic material with long stability and more resistant to ambient conditions and more economic to synthesize than the traditional antibody. The enzymatic assay used to go with an electronic mediator molecule. It is because the active center of the enzyme is hidden in a 3D structure, and this avoids the electron transfer to the electrode surface. Therefore, there is a trend to perform enzymatic assay with direct electron transfer. Now, I would like to do reference to my personal experience developing electrochemical biosensor toward the addressing of point-of-care device requirement. This is an electrochemical immunosensor for human NMP9 detection performed on commercial screen-printed electrode and with a labeled sandwich format. Here, gold nanoparticles are used as electrochemical label and carry of the second antibody as well. The electrochemical detection of gold is based on a chemical oxidation with acid solution assisted by an electrooxidation at high potential to subsequently measure the reduction of the previously oxidized atoms. For the first time, the environmental friendly and occupationally safe sodium nitrate and sodium chloride was evaluated as potential alternative to acid solution traditionally used for gold nanoparticle electrooxidation. In addition, a new strategy to improve the sensitivity of the biosensor by citrate PEG ligand exchange was presented. Changing the citrate by PET ligand, the size of the conjugates increase as corroborated by DLA's measurement, and also it produces less compact and easier to oxidize gold nanoparticle immunoconjugate. The calibration curves obtained for different immunosensors during human NMP9 detection demonstrated that the combination of sodium nitrite for the electrochemical oxidation of gold nanoparticles and the PEG ligand exchange produced similar sensitive response than that using acid chloride as oxidant and citrate ligand for gold nanoparticle stabilization. The biosensor was tested for human matrix metallopeptidase NICE analysis in spiked human plasma exhibiting good recoveries. These results show that the device developed is applicable to the analysis of protein biomarker in blood plasma and could contribute to the development of more environmental friendly gold nanoparticle based electrochemical biosensor. The direct electrotransfer between the electrode and the redox enzyme immobilized on it is difficult to achieve due to the complexity of the 3D protein structure, where the redox center used to be unreachable, so in many cases is useful an electromediator molecule. 3D printing is becoming a widely used alternative in electrochemistry to cheaply produce custom-made cells, electrodes, and biosensor devices. In this world, additive 3D printing has been used to produce graphene electrodes and turn them into a very simple biosensor. The 3D graphene electrode is chemically and electrochemically activated and subsequently functionalized by physicochemical adsorption with gold nanoparticle and the HRP enzyme. The chemical and electrochemical activation of the electrode made it possible to notably improve their electrical property as shown with the increment in current in the cyclic voltammetric curve obtained before and after the treatment. This allowed to use of the electrode as a platform for the direct immobilization of the HRP enzyme, achieving a good direct electrotransfer between the shards that are generated in the enzyme toward the surface of the electrode. Analyzing the hydrogen peroxide detection at different stages of the biosensor fabrication, we found that significant changes of current were observed when the enzyme is present in the biosensor composition, compared to non-enzyme. It demonstrated that the current intensity change observed was caused by the enzyme's electrocatalytic activity and its interaction with the activated 3D printed electrode. The incorporation of gold nanoparticles produced an enhancement of the sensitivity and the electrotransfer between the enzyme and the electrode compared with the rest of the sensor, reaching a limited dose detection comparable to similar systems reported before, and a repeatability of 7%. The long-term stability of the biosensor was evaluated and his concerned the 84% of his initial response after 5 days. The effect of the interference was negligible compared with the current change generated by the initial and final hydrogen peroxide addition. The recovery of the activated electrode with SRP enzyme and with gold nanoparticles plus SRP enzyme biosensor were around 98 and 87.5% for 25 and 50 micromolar of hydrogen peroxide. Finally, I would like to be grateful to the people and the principal research that support me at different research centers, and of course to all of you for your kind attention.